Good afternoon, everyone. So let's start with the week 8 of RL. Today we'll cover with the Q learning, which we have basically left last week. And then we'll go to the eligibility traces, forward view, backward view, and all. So let's start. Let me share my screen. The recording is on. Yes. First of all, what is Q learning? Let us start with what is Q learning. Then we'll see the like difference between the Q, like we'll see the code, we'll dry run that example. Then we'll see what is SARSA, see the difference between them. And then I think that will be the better understanding of the Q learning as well as the SARSA. First of all, Q learning is off policy reinforcement learning. What do you mean by off policy? In the last lecture, we have studied there are two types of RL, off policy RL as well as on policy RL. What do we mean by off policy RL? The question arises. And then what is the why Q learning is off policy RL, not on policy RL? I'll tell you. Q learning is off policy RL because it learns the optimal policy independent of the agent's current policy. If it is learning from that particular policy only, then we'll say that it is on policy. If it is learning from the policy which is independent of the agent policy, then it is an off policy. If I talk about Q learning, it is an off policy here. I think in the last lecture, we have covered about this. Let's go back again and then see. These are rollouts which we have done. And before that only, we have done about on policy as well as the off policy. Evaluate and improve the target policy while following a different behavior policy. That is what I want to show you again. So off policy Monte Carlo is we are evaluating and improving the target policy while following a behavior policy. And what is the target policy? Target policy is the policy which agent wants to learn, and behavior policy, it is used to generate episodes for the exploration. Basically, it is a different policy. It is not the same policy with the agent which the agent is following. So I can say that it learns the optimal policy independent of agent's current policy. If it is learning the policy independent of agent's current policy, we can name it as off policy. And Q learning is doing so. So we can say that Q learning is an off policy reinforcement learning. If I talk about how we'll update the Q learning, we have a Q learning update. If I have state, I have an action. QSA plus alpha R plus gamma into max of A QS dash A minus SA. What is QSA here? This is the Q learning update. So what is the QSA here? I can say it is a current estimate of state action pair. Alpha, we know that it is a learning rate. R, the immediate reward. And if I talk about max, say QSA, it is max estimated value over all possible actions. In next state S dash. So what is the rule here? What is the rule in Q learning? It choose the maximum Q values. As mentioned, what it is doing, it is choosing the maximum Q values from the next state, max A, QS dash A, rather than Q value associated with the next action. By agent's current policy. I'll explain you step by step, and I'll also give you an example which we'll dry run it and also we'll code it for the Q learning. So let's go through again. What is Q learning? Off policy. Why it is off policy? What is our rule saying? It chooses the maximum Q values from the next max of QSA rather than the Q value associated with the next action. It is not choosing the Q value which is associated with the action by the agent's current policy, rather than it is choosing the maximum Q value, as we can see in our equation. This is the current estimate, and this is the learning rate, this is the immediate reward, and it is choosing the maximum estimate value. So that is why it is called as an off policy reinforcement learning. Any doubts? Yes. I got your mail. Am I audible first of all?
I can hear you. Yes.
Yes. I got your mail. We'll discuss about it after the lecture.
Okay. Okay. No problem. Thanks.
Any doubts until now? You got this concept of the Q learning?
Mm-hmm.
So let me give the step-by-step explanation. What we'll do in practice, first of all, we'll initialize the Q table with zeros for all state action pair. What is this Q table? If I talk about this Q table, it is also a data structure, we can say, that stores the estimated value of this state action pair. That is what we are doing. That agent is using for the decision. So first of all, first step is initialize the Q table with all the zeros with it. Then the next steps come exploration. We'll choose the state S and select the action A on current policy. How we'll do that? How we'll select this action A on the current policy by choosing the state action, by choosing the state epsilon greedy or some other approach, as we have done this epsilon greedy, and I have also explained in detail with the code. So we can do that. And the next thing is, I can name it as interaction. We'll observe the intermediate reward. And then update the last value, last point, we'll update the Q value. How we'll update? By this position. Alpha decay R plus gamma max of Q of SA minus Q of SA. Then we'll update the state. Then we'll repeat until the convergence also. So this is the same thing, just we have initialized the Q table by the zeros, then we are exploring by the epsilon greedy, and then we are observing the reward and then updating the Q value. So let us take an example to dig deep in this Q learning concept. Like a professor has also taken this example. I think we'll take the toy example rather than cliff example, which is in the book also. So let's take a toy example rather than the old example so that we can dry run these iterations and see what is happening actually. The typical cliff example is this is the starting state, this is the goal, and this is the cliff. And what is the policy? Basically, agent is wandering over the agent wanders over the cliff. If he he's going to get the reward if he wanders over the, this is the cliff basically. I'll mark it as, this one is the cliff basically. And if the agent wanders over the cliff, the agent will get the reward of -100. And otherwise, wherever it will move, it will get the reward of -1. We are given with the starting state and we are given with the goal state, which is G. And the agent has to reach from the starting state to the goal state as soon as possible, as quickly as possible. That is what the main goal, what is the main objective here. So for the toy example to solve, let us take it toy example of this cliff example only. So what we'll take, rather than taking so much of states, we'll take this state and then a cliff and then goal 3 only. And then here. So we have the coordinates 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Or if I want to show it like that only, it is like this. This is the starting state, this is the goal state, this is the cliff, and we have to reach from starting state to goal state. I'm doing this toy example so that we can solve it easily and we can get a better view. So S here stands for the start state, 0, 0. G here stands for the goal state, 0, 2. C here stands for the cliff, 0, 1. And 0 here is the 0 which I have mentioned here. They are the safe states. What are the parameters? If I talk about the actions here, we can move up, down, left, or right. Alpha, the decay parameter, let us take it as 0.5, and gamma, let us take it as 0.9 discount factor. As I have mentioned earlier also, as it is in the book example, we'll take same only. We'll take the reward -1 for each step and -100 if for falling in cliff, we can say. So what are the step? Initialize the Q table with all zeros. So let us do first step, Q table. So 0, 0, up, down, left, and right. What are the states? 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Currently, the Q table will initialize by zeros here. Now, what is the next step? Choose the state S and select the action A on the current policy. So let's start from our episodes as we have done in the previous class only. Episode 1, start in state 0, 0, 0. We'll choose an action. By epsilon greedy. Why we are doing so epsilon greedy? So that we can do exploration as well with the exploitation. As I have mentioned in the earlier lectures of the MAB also, like if I take the epsilon as 0.1, which means 10% of time I'll explore and 90% of time I'll exploit. Why I'm not doing greedy here? Because if I'll do greedy, then only I'll exploit and I can also result in the suboptimal solution. To go in the optimal solution, I'm doing exploration as well as exploitation. So we are taking just 0.1 this so that 90% will go with the greedy approach, whatever is the max. But 10% of time we'll also explore the other like arms or actions. So we are choosing an action with the epsilon greedy. Suppose we move to the state. We are in 0, 0. Suppose we through epsilon greedy, it has told us, let us move right. And we move to the state 0, 1. If we are in the state S, and if we move in the state 0, 1, it means that we'll fall in the cliff. And as the step 3 says, first you will do initialize zeros. Second step we have done, choose the state and select the action. Third step say what is the observe intermediate, observe the intermediate reward. And here, if we'll fall into the cliff, the intermediate reward is minus 100 as told in the question. And then we'll update the Q value. Q00 and SA, I'm writing 00 is the state, and action we are taking it as right action, and plus alpha. Alpha we have taken 0.5 here. Reward is minus 100 plus gamma 0.9, max of QA, initializing with zeros only, minus 0 here. So here this is 0 plus 0.5 into minus 100, which became at minus 50. So now we'll update our Q table, that if we are in 0, 0, and if we'll move to the right, then we'll update it as minus 50. Let us go to the episode 2 now. Any doubts till now?
Yes, I can ask one question. I was just thinking that I understand this thing that Q table means Q action paired, but my question is that suppose in reality that means we need to explore, means we need to consider in reality when we will make the Q table, then there are as many as combinatorics is possible. We have to consider all the things, means it's required huge computational power, right?
Yes, this is the like if we talk about NDP, that is the main we can say this lookup tables or this Q tables or lookup tables. They are the main limitation, that it is having computational power. It is consuming the computational complexity. But if we compare this Q table, compare it with this value iteration method or MDP that we have done before, model based. There are two types. One is model based, one is model free. Model based is I am in the state S, I'm going to actions. I'm performing some actions. When I perform every action, then I'll know that this is the state, this was the best action. Wait a second. I'll tell you. If I talk
Your voice is off, means I cannot hear you.
if I compare with model free, they are less model based. If I do value iteration MDP approach, which is the model based, it means if I'm in a particular state, I'll perform action. I'll perform all the actions, and then I'll choose which is the optimal action. Action 1, action 2, action 3. Then I'll choose which is the optimal action. And I'll do till end, till terminal state. And there'll be some randomness also, which is called a stochastic environment I'm having, I can say. Then I'll go to the terminal state. Then I'll maintain a table, which will say that this is a policy here, that if I'm in this state, then this action has to be performed. If I'm in this state, this action has to be performed. This is I'll do after every, at the end I'll maintain, and then I'll do. This is an offline thing, I can say, or it is not considered the proper part of RL also sometimes, this MDP thing. And then it is very computationally heavy, because suppose I have this is 2 power n complexity. And if I compare Q learning with it, Q learning is also computationally heavy as compared to other algorithms sometimes, because we are maintaining this table. Yes, it is computationally complex. But if we compare to the model-based approaches, it is lesser computationally complex, as we are updating side by side.
Yes.
You got it?
Is there any much more easier method? No, no.
Yes, we'll go ahead and then see what are the replacement of these lookup tables.
Okay. Mhm.
You're doing RL for the first time, or
No,
you have
first time. Actually, I didn't do RL previously. That is the problem.
okay. I'm also at the initial stages only. Okay.
Okay. Actually, I mean, every day I cannot follow you as I wrote. Means there are some, works and all these things. So anyway, but your lecture is really good. Means even I saw in YouTube. Anyway.
Okay. So, where were we? I lost the plot. Huh? So here, this example, you got it. What we are doing.
Yes, I got it.
So this was just in episode 1. So let's move to episode 2 for the more clarity and then check it. So let's start in this state 0, 0. Let's now suppose epsilon greedy gave me move down action, and then I move to 1, 0. I'll move to any state other than cliff. I'll get the reward of -1. So I'll update the Q value, Q plus alpha, reward that is -1 plus gamma, which is the discounted factor, into Q max, which is already now 0 only earlier. Then we got it -0.5. And we'll update it like if I am in 0, 0, and if I'll go down 0, 0, I'll go down, then 0.5 -0.5, I'll get the reward Q table as. Now we'll not stop because we haven't entered into cliff. I'll update the state as mentioned after Q. If I'll go to the steps, initialize the Q value, explore it, observe the intermediate reward, update the Q value, and then state update. State update we are doing in the last episode. We entered into the cliff only, so that is why we stopped there. But here we didn't enter to cliff, and then we are updating the state. Now in the updating state, if we are going from 0, 0 and down, we are now in the state 1, 0. Suppose in the state 1, 0, epsilon greedy gave me that right is the action which I have to perform. Right means that is 1, 1. Again, I'll get the reward of change. Again, I'll get the reward of -1 here. And again, I'll update this. Now I'll update 1, 0 as I was in 1, 0 and I took right here. So if I'm in 1, 0, right, get -0.5, the Q value. So this is the process which I'll continue over the time I learn the optimal policy. This is the whole Q learning thing. Let us now go for the code part so that you can understand it well through the code. The simple cliff example I have coded. Go to the main code. I have run it for the multiple episodes. First of all, for episode in range of n episodes, starting state, Start, I have mentioned here 0, 0. So I'm starting from the state, I'm initializing to state. While state is not equal to goal, action index is equal to epsilon greedy policy state. I'm giving the state parameter. Let's go to this epsilon greedy policy. As we have done this epsilon greedy code before also, I'm choosing a random number. If it is less than epsilon, then I'll basically explore. If it is more than, then I'll basically exploit and choose this argmax here. And then I'll get this action index, which action basically to perform. Next state is equal to take action state and action index. I'm giving it to that. Take action means the action which is performed there. Next state means, like, suppose I'm in the 0, 0 and I'm taking right, then what will be the next state here? That is what I'm doing. If the next state in the cliff, then I'm giving the reward minus 100. And then I'm starting it from like again, as I have done like in episode 1, it was on the cliff. I gave the reward minus 100, and then I started the next episode. If the next state is not in the cliff, I'm giving the reward minus 1. And the target, then I'm updating the Q value. This is simple. Target is equal to reward plus gamma into np.max, and then updating. The same thing. Q table, I'm updating it. And the state is equal to next state. And then I'm running it for the multiple episodes. And here, I think this count. I forgot to put this function in. Okay. I'm running it multiple times until I'm getting to the optimal state.
So for updating Qtable, I mean, in reinforcement learning, we always need to write the code. Means like other model in machine learning, we can means import some library and write. Means here, is there any other?
No. Like in machine learning, there are some, I think, I want to say this. Like instead of Python, also we have some inbuilt like libraries or something. But yeah, we have to do like in Q learning. I can share this code with you as well.
Okay, then that will be great because I want to practice it as well. So
yes.
You can please.
I'll share this code and the other collaborative collab notebooks as well, which contains like value iteration and that this greedy, epsilon greedy, Thompson sampling, all the codes.
Okay. Okay.
Yes.
Thank you.
You got the intuition behind the code. What is done? The same thing which I have like dry
Yes, it is easy. I understand it is no problem.
So next, let's go to eligibility traces. Earlier we have done TD0, temporal difference 0. Now we are going to move to TD lambda. If I talk about the return here, Monte Carlo method, RT plus 1, return at time t plus 1, plus gamma into discount factor into return time t plus 2, plus gamma square into return time t plus 3, and so on. This is basically the full return, we can say, which we are getting in the Monte Carlo method. If I talk about in TD method, that is the temporal difference, RT plus 1 plus gamma B ST plus 1. This is GT1 here. Or we can say, this we have covered already, how it came, the TD, like the return in the TD learning, that is temporal difference, as well as in the Monte Carlo. And then this we can also say as one step return Or we can say one step truncated corrected return. One step return is this, then truncated corrected return, like corrected return, we are adding it and truncating it. That is what it is saying. We truncated the full return. I can say but I corrected it by adding BST plus 1. That is why its name is one step truncated corrected return. If I talk about two step truncated corrected return, I can say RT plus 1, RT plus 2. This is two-step return. If I say two-step truncated corrected return, that is VST plus 2. So I can also write for n-step truncated corrected return. There might be some tasks where definition of return other than TD return do well, some tasks where the full return do well. So there is a confusion that what should be n here, like two-step truncated return, one-step truncated return. First of all, let's understand what is online RN versus what is offline RN. If I say I wait till n steps and then we make the update. This is basically a GT of n. Here, reward 1, reward 2, two-step I'm doing the reward and then we are doing here what I'm saying, I'm waiting till n steps and then we are making the update. That is GT of n. Now talking about offline. Regardless of when we finish n steps, end of the episode, I'll make the update. This is basically the offline one. Online one, I'll make the updates. If it is GT1, I'll make the updates after one step. Offline is after the end of the episode, I'll make the updates. So what are the changes we'll see in offline update and online update? If I visit the state, second time in the trajectory, if I say, or I can say I'll revisit the state. If I talk about the online one, I'll use new value function here. Because the second time, I'll compute this GT2 value. It will be the one which is the changed value after the first time I computed this GT2. Basically, if I am talking about the online one, if I'm using the I'm visiting the state the next time or I'm revisiting the state, first time I'll visit the GT2, and then the second time I'll visit the GT2. The second time the value will be changed in the GT2. But in offline, I can say that we'll have the same value, same V. Now, similarly, as I have told earlier also, there are some cases where offline will perform better. There are some cases where online will perform better. In Rux, I can say offline is at the end of each episode, we'll update the value once. I can say that at the end of the episode, update the value once. And online, we'll update the value each time we go from that, or after the n steps, we'll update the value. Like if GTN is there, after n steps, we'll update it. GT1, then 1 step. So every time here in online, every time I will make an update, I will change the value function. By delta. If I'm saying online, what does it mean? I'll change the value function. If I'm saying I'm taking GT of n, any n, so delta VT of S, it will be 0 until n steps. After n steps, delta VT of S is equal to as we have done this earlier also. That's how we have to update it. GT of n minus VT of S. So updation of the value function will be after the n steps. If I talk about offline, I'll tell again. After n steps, I'm making the changes. If it is GT of n in online, offline, don't make any change. Until episode comes to end. At the end of episode, I'll sum up this and make the change. This is the difference between online and offline. Now, coming to eligibility traces from where we started. It comes from behavioral psychology, basically. Basically, people in psychology, they started talking what kind of stimuli, I can say, is causing a particular behavior. And so which kind of stimuli I can say is more eligible for this particular behavior? Like suppose someone is eating food and there is a bell ringing and there is a light we have to on. If the bell rang 5 minutes ago, like before also, we'll first switch on the light rather than going to bed. So basically, which is eligible, we can say. The stimuli which is eligible for any change that comes out of this behavior. That is what it is inspired from, or we can say it comes from. Or things which are more proximal, we can say they are more eligible. So, suppose this is a stimulus. Here I'll get the reward. This is another stimulus. This is they are decaying here. This is, so whichever is more eligible, that is which we'll choose. One way, like what I'm saying is it will decay over the time, and the point where I'll get this reward, whichever stimulus is having higher eligibility will get the higher update, I would say. So if suppose this stimulus only, choose another color here. So the frequency it occurs once more, the stimulus, this red one. Then we can say it is more important, or this status or this stimulus is more important. So what I'm doing is, I start a trace that is decaying, that keeps on decaying with time. The point where the reward is occurring, whichever the stimulus is having higher eligibility, will get higher update. And as we are saying it, if it occurs multiple times, like if in this case only, if occur more than one time, more time, then we can say it is more important. So here in the eligibility trace, we have two views here. One is backward view and one is forward view. Backward view is look at when reward happen and then look at due to which states they are happened. Forward view is this, we are having the states, what are the future expected reward for that state? You got the idea by the names only, what are the backward view and what are the forward. So now I have GP of lambda, which is a new notion. Of lambda return, we can say, like we were talking about this. So I told you about one-step return, two-step return, then I'm truncating it with the, like I'm correcting it by truncating it VST plus 1. Suppose if I talk about GP of lambda, what does GP of lambda indicates? Suppose I'm going to take this, like earlier I was talking two-step, one step. I'm going to take 0.5 instead of taking either one step return or two-step return. basically what I'm trying to do is I'm using some kind of average of the two. So GT of lambda, now I can write this 0.5 GT of 1 plus 0.5 GT of 2. Or I can also do like this. If I'm thinking that I can do 0.5, I can also do like this. 0.33 GT of 1 plus 0.33 GT of 2 plus 0.33 GT of lambda. 3 I can say. So can I think of generalizing? Let's not write this 0.1, 0.2. GT of 1 plus lambda GT of 2 plus lambda square GT of 3 and so on. But here, as we are doing the weighted average, as we know that while doing this, the weighted average notion or the weighted average of n step returns also, the sum should be equal to 1.
Excuse me, what
Yes.
we have written just above GT of lambda, before that GT of what it is? GT of?
Where?
Just is means GT of lambda, the last step GT of lambda, before that GT of what?
GT of lambda only I am writing it here.
Okay, all right. Okay.
Just writing here, I can also do, this is a weighted average, like I can give half average to both of them or
Got
average.
it. Huh.
And they should sum up to 1 because I'm doing this weighted average for the multiple returns. And suppose that first thing they should sum to 1. If suppose they are not summing up to 1, I can say that they're overestimating. If they're going more than 1, they're overestimating the return I also. So that they can sum up to 1, what I'm doing here is multiplying with 1 minus lambda. Or I can generalize it and write it. Lambda n minus 1 gt of n. I can write it like this. Suppose the episode terminates at this point. Suppose the episode terminates at this point. Then we can say then again the sum will not equal to 1. Then what? What about this part? We are not including this part. And if we are saying that the episode, we are talking about the offline view, and the episode terminates up to episode stops here. Then what we'll do? So that is why we are updating this equation and writing it as in this part we are saying this thing, and next part we are just adding this GTs here. And it is offline here as we need the GT. So this was the backward view, which we have, forward view. And then now we'll go with the backward eligibility, how we'll go back and then see. Now I'll tell you, I'll introduce this eligibility term again, and I haven't introduced it, I think. I've just given you the intuition behind it. I'll introduce this, what is this eligibility term and how we'll do it. As we have done here, that when a state is repeated again, we are increasing the eligibility of the state. So that is what the main thing is. Whenever a state occurs, let us say S1 has occurred, increase the eligibility of S1. Now, what is this eligibility and how we are doing it, how we are decaying it, and how what is happening as we have done that. Suppose the eligibility is like this and we are decaying the eligibility, how it is happening. ET of S is equal to gamma lambda, as we have done, ET minus 1 S. If the state is not equal to S, gamma lambda ET minus 1 into S plus 1 if ST is equal to the particular state we are thinking of. What it is saying is that state eligibility is gamma lambda times the previous eligibility. Or I can write it as, if I'm writing a tuple, if I'm in state S and performing action A, gamma lambda ET minus 1 SA plus 1 if ST is equal to S and AT is equal to A. Talking about this gamma lambda, what it is, this is the decayed eligibility trace. I'm decaying the eligibility trace from the previous step. If I talk about this gamma, we know that this is a discount factor. Lambda, this is the trace decay parameter which is used here for decaying. And if I talk about ET minus 1 SA gamma lambda, what does this means? That past state action diminishes over time. What does this mean? If I'm saying gamma lambda ET minus 1 SA, it means that the previous actions are diminishing. We are giving more credit to the recent experience or the recent actions, we can say. I'll come again to that formula in a minute. First of all, I'm telling you about this term. We are more crediting or giving, I can say, more importance to the recent or new experiences or the actions performed. Now, we have learned what is this gamma lambda ET minus 1 SA. We are giving more importance to the recent one, lesser importance to the the current one, the previous one. What does this mean? Plus 1 STA ATA is equal to A. It means that current state is equal to the, I can say, specific state S and A, we are updating the eligibility traces, or we can say if the current state pair is SA, the eligibility traces increment to 1 here after the decay. If it is not that particular state, then we are not incrementing it, we are only decaying it. If it is equal to SA, we are decaying it and then updating, or we can say incrementing it to 1. So we have here two types of traces: the accumulating traces and the other one is replacing traces. Accumulating traces, what does it mean? What I'm doing is, I'm accumulating. If I'm saying that if I'm in the current state SA, the eligibility traces, they are incrementing it to 1, or we can say that I'm accumulating the traces. And if talking about the replacing traces, I am basically replacing it to 1 here. I'll give you over a minute, just in a second. Maybe I have some pictorial representation. Not sure about it. No, I'm not having. Okay, I'll give you what I mean to say about accumulating traces. When agent visits state action pair, the eligibility trace for that pair is incrementing by 1, as we have seen. Now, why its name is accumulating traces? If I am visiting state action multiple times within an episode, they are incrementing by 1, or I can say the eligibility trace are accumulating. If I talk about replacing, this is basically accumulating trace. When agent is visiting, the eligibility trace is incrementing by 1, or they are accumulating the eligibility trace. If I talk about replacing traces, what happens in replacing traces? When agent is visiting state action pair, eligibility trace for that pair, it will set to 1. Like in accumulating traces, we are incrementing the eligibility trace. Here we are setting it to 1, regardless of the previous values. So this means that if the state action pair, it is visited multiple times within an episode, the eligibility trace is replaced by 1 each time. So that is why we are naming it as replacing traces. Any doubts?
No, so far it's okay. No issue.
Okay, let's move forward. So backward view, here we can say it can be online as well as it can be offline here. Offline means I have to wait till the end of the episode and add all delta VT, submit all delta VT and change in one go. And suppose suppose we suspect that it is not going to be more important after one or two steps. Like after one or two steps, it is not important to go into the future. Lambda then should be very small so that it can quickly decay, decay up. These are the few points. And suppose I have large state space. And I don't want to keep updating the eligibility trace. In every step, because I'm having so many of states, if I update it, as you mentioned the point, it will be very computationally heavy or complex. So I don't want in every step to keep updating it. So I can make it as 0, the lambda part. And if I make lambda is equal to 0, we again get TD 0, as we have done in the previous class. We have done exhaustively what is TD 0 and how it works. I think we have done dry run it also. And suppose what happens if I make lambda is equal to 1 and TD 1. Sorry, what happens if I'm taking TD 1 and I'm taking gamma is equal to 1? Gamma is equal to 1 is a discount factor, as we know. So there are many limitations. If I'll take gamma is equal to 1, that is the discount factor is equal to 1. In many cases, what the discount factor we are taking as 1 when we are giving the equal importance to all the states. But in some cases, we have to give more importance to the states which are nearby rather than the states which we have crossed so far, or the previous, we can say. We want to make in the trajectory, we want to give more importance to the newly or recently one. So that is why we use this gamma here. But in TD1, there is a limitation that we can't use the gamma is equal to 1 because it will lead to instability as well as it will not converge here. If I talk about TD1 or TD here, TD learning here, what is TD learning? As we have discussed, it uses bootstrapping. In the previous class, we only discussed what is bootstrapping and how it is proceed basically. Here, the value function is updated using the estimates of the future value functions, we can say. This is called bootstrapping. The next one we can say and if we compare it with Monte Carlo, it is more sample efficient. As it is learning incrementally. Then now gamma is equal to 1. It means it reduces the impact of future, rather than saying future states, I can say future reward. Sorry for the states here, future reward. It is reducing the impact of the future reward because it is giving the equal importance to all the steps. So here, as we know, what is TD error here? So TD error will grow rapidly and it can impact the future rewards, which like as it is not discounted here. When this was lambda is equal to 1 here, that is in TD 1 here. This was the normal TD case I was talking about. Now, if the lambda is equal to 1, what is in TD 1? Agent is assigning full credit to previous state action. Here, that is leading to the current reward, I can say. Now, if I do gamma and lambda is equal to 1, the algorithm assigns full credit to previous state action pair and it doesn't discount the future reward. It may be highly insensitive and it may lead to large update can cause, basically we are having it can cause instability. And on the other side, it can also cause the convergence issue as the balance is disrupted between this exploration also and the stability as well. So that is why when we are talking about this gamma is equal to like lambda is equal to 1, the gamma is equal to 1 is not advisable to take because it is leading to instability as well as convergence issue of this bootstrapping nature of this TD1 learning. I think we can take 10 minutes of rest and we can proceed our class. 6:20.
Okay. Okay. Mhm.
Any doubts till now?
No doubts.
Let us now proceed the class. Am I audible?
Yes.
Before starting the control for SARS, lambda and all, we'll revise the concept of first. Let's revise what is the difference between SARSA and Q learning and what are basically these. What do you mean by SARSA here? SARSA here refers to state, action, reward, next state, and next action. If I talk about SARSA, unlike Q learning, it is an on policy algorithm. What is online policy algorithm? It learns the Q value based on the same policy it follows. When I was talking about Q learning, it was having we were talking about the max Q values, and we were saying it will not follow the same, like it will not like learn the Q values based on the same policy it is following. That is off policy algorithm. If I talk about SARSA, it is on policy algorithm. And the update rule for SARSA, same like Q learning. The difference is rather than max, it is following the Q, it is having the Q which is following the same policy. It is following that Q. It is learning that Q. I mean. So alpha here is the learning rate. Gamma here is the discount factor, determining the importance of the future reward, I can say. Alpha, which is controlling the weight, which is given to the new information. And if I talk about the exploration strategy, we are using epsilon greedy for this exploration strategy. And the action with the highest Q value with probability 1 minus epsilon and selecting randomly the epsilon 1 probability, as we have done in epsilon greedy. Talking about the Q learning, Q learning is off policy algorithm. We have done in this class only that it is independent of the policy it follows while exploring the environment. Basically, here the agent is choosing the optimal Q values regardless of the policy which it is following during exploration. The agent is choosing the same action, same Q value based on the same policy it is following, whereas it is choosing the Q value independent of the action policy which is following. So that is why it is off policy. We have done the update rule. Now comparing the first comparison, we got it from the definition itself. On policy versus off policy. That Q learning based on policy, and SARSA is based on policy, and Q learning is based on the off policy. Talking about exploration strategy. Both algorithms are using epsilon greedy exploration strategy. Though, if I talk about SARSA, it is depending on the exploration policy, while Q-learning update policy is not, because updates are not, because they are following the like not the same policy while updating the Q value. If I talk about the convergence, Q-learning will converge to the optimal policy. While if I talk about SARSA, it may or may not converge, or I can say near optimal policy it can converge. Talking about the behavior, SARSA, if I talk, it is, I can say it is conservative in its exploration, while Q-learning is more aggressive if I talk about this exploration part. So that is why I'm saying that Q-learning is more efficient in some like environment, and we can say that it is reaching to the optimal results. So main difference, what we learned, that SARSA is based on policy and Q-learning is based on off policy. Q-learning learns the optimal policy independent of the exploration strategy, I can say. So talking about now controls, coming back to the controls. Accumulating traces, as we have done, ET minus 1, SA plus 1. If ST is equal to S and AT is equal to A, otherwise will not add up. If ST is not equal to S and AT is not equal to A, we will not increment it by 1. If I talk about the replacing traces, it will be equal to 1, not depending on the previous value, what it was, if ST is equal to S and AT is equal to A. While talking about the state action pair, suppose I have S, I perform A, go to some state and perform A2. Now, policy suppose keeps taking A1, suppose. A1, it takes many times. And then it choose the A2. Suppose the reward here is 0 and here the reward is 1. And it choose A2 and got the reward of plus 1. So what my policy is saying, that I take A1 many times and I'll take A2, and then after taking A2, I'll get the reward 1, suppose. Now, if I talk about the accumulating traces, what I can say, it is gamma lambda. I can sum it like this and say it is gamma lambda of t. It can happen that it can be much larger than 1. So when I'll reach at A2, I'll get 1. The trace of A2 is 1. I'll think that A1 is better, and next time I will come to state S1. I'll come to state S. I'll more likely that I'll take A1, and then same thing will happen. So in this case, I can say when we are doing the control, accumulating traces are behaving bad when we are doing that control, or we can say replacing traces are better. There is another version, or we can say aggressive version of these replacing traces. Like suppose I'm in state S, I'm performing A1 and then A2, getting the reward 1, getting the reward 0. So whatever I do in A2 should go and update the value for that only. It shouldn't affect the other actions. What I'm saying is, if I talk about the this replacing trace, what I mean is that it will be 1 if a second if st is equal to s and at is equal to a, and on the other side it will be 0 if st is equal to s and at is not equal to a. It shouldn't affect the other actions, I can say. That is what how it behaves, the aggressive version. Now going to Q lambda Witkins. This was the Sarsa lambda which I was talking about. I can say only the Q lambda thing. What we are doing is here, ST is equal to RT plus 1. I have written it earlier also, this update equation of this Q learning. Simply writing that only. In Sarsa, we are not taking this max. We are following the policy only, the same policy only. We are taking the max. What I'm saying is, if I'm in the state S, I'm taking A, going to state S dash, and then I'm choosing the max A dash. Then I'm choosing the max A double dash. The first one was the simple one because I'm having SA. So here I can say that I'm following the greedy policy here. So greedy trajectory is the assumption that is made in the Q, that is in the Q learning. But if we talk about it, we also have to explore rather than doing like we have done this exploitation before also, that if we'll not explore, we'll stuck in something that is if we'll follow always the greedy policy, we'll stuck in something that is suboptimal in nature. So what we are doing here is, what is the solution here? First I'll write this and then I'll explain. TSA the same accumulating one if ST is equal to S, AT is equal to A, and AT is equal to argmax of A dash, Q of ST dash and A, and gamma lambda ET minus 1. If for all others, I can say if the action is not equal to A and AT is equal to basically argmax and 0 if AT is not equal to argmax. What I'm saying here is, keep accumulating eligibility Am I audible?
Yes, now we were audible.
I think I was disconnected. A second. Is my screen visible?
Yes, I can see.
If I talk about the lookup table, it is a representation of the value function. But we have some drawbacks. Can you tell me the drawbacks of the lookup table? Computationally heavy, as you told me earlier.
Means that is
Memory, I can say. So suppose that if I'm not talking about memory, now like or memory, or we can also say the continuous states. Okay, I'll not touch that topic now. So instead of having the lookup table, what I can talk about is about the functions. If I talk about ML part, like we are using the parameters and then we are trying to estimate that parameters. That is what we are doing. We are given some data points and we are trying to induce some function. If I talk about table, this lookup table, I can say unless I have visited the state often enough, I don't have an estimate for the value function. Means to get the estimate of the value function, I have to visit that state many times. And suppose I have many states in millions. And if I am having that lookup table and I have to visit that same state many times, it will be very tough. It will be very computationally heavy. So instead of representing value function, basically we need to generalize. Instead of representing value function as lookup table, we can represent it as some kind of parameterized function. Like in deep neural networks, in neural networks only, what we are doing is the same only. Lookup table itself is a parameterized representation. If I say, so if I talk about parameterized representation, as we have discussed, there are limitations. If I'll take this lookup table, the computationally complex one, I have to visit the same state many times. And if the states are in the millions or billions, then it will be very tough. And reaching one state at a particular time, it will not be enough because I have to reach that state multiple of times so that I can get a good estimate of the value function and I can get the optimal result here. If I talk about the parameterized representation, like parameterized representation, if I talk about it, it also comes up with some cost. If I make this parameterized representation means the neural networks or so, and the parameters in the neural networks are the weights of the neural networks. If I make this parameterized representation, suppose a complex one, a very complex one, so that I can get a good value function. I can get a value function without any loss. I'll write it and then explain. If I make this parameterized representation, suppose complex enough, that I can represent my value function without any loss. Then there will be again a difficulty, because then the number of parameters, if I want it totally I want a very good value function which should be without any loss, then the number of parameters will just will be the same, or I'm making it so complex that the number of parameters is same as number of states in lookup table, then there is no use of this parameterized function. So I have to accept approximation. That is what most of the RL algorithms which we'll study further will do. You can't model every value function. So now we come up with the function approximation thing. Suppose this v pi is the true value. This v pi is basically the true value function, and then we are approximating this value function. Here we are, this is the set of the parameters basically. So the question arises, what should be the criteria on deciding what v hat should be? So this is the question which arises when we are doing the function approximation. What should be the criteria to choose that function? There's two stages to answer it. First stage says how the output is going to depend on that theta, basically this set of parameters. Describe it in detail. If I'm talking about neural networks, suppose I have this, I'll have here the weights here. Then how the weights will define by this will define this value function, that what Vs should be. So that is why I'm saying how output is going to depend on theta here. Basically, there are three things which we have to take in mind, like while choosing it. Find the family of the function. I can say that I am considering. Like suppose which family of the function, neural network, decision tree, which family of the function I should choose. Figure out the error measure. Now, what is this error measure is? How close I can say my estimate is to true value function v pi. This is how we are calculating the error always. So what should be the error measure? Or I can say what performance measure I should use. Or I can say how I define this theta here parameter so that it can minimize my error measure here when I'm doing this function approximation. This is the third point, like how I'm going to find the theta. that is going to give me good approximation. So what I'm saying here is, like while choosing it, we have to take the three steps are there. First of all, which family of the function I have to choose. Second is error measure. We'll talk about the error in detail. How to choose my estimate, how to choose that. Basically, what performance measure I should use here, and how I'm going to find the theta that is going to give me the good approximation here. You might have heard about this mean square error. If I talk about this mean square error, it is nothing but 1 by n, the actual value minus the true value, estimated value minus the true value, square, mean square error. This is what it is. So this term is basically multiplied by 1 by n. 1 by n, it is also studied in ML, machine learning, that we are multiplying it by 1 by n by giving equal weightage to all of them. But here, if I'll talk about RL, what we are doing is, we are multiplying by d pi of s. If I talk about MDP, Markov decision project, Markov decision process trajectory, if I'll follow policy pi, I'll end up in Markov chain here. Markov chain is, I'm taking some steps as we have studied earlier also. And as t tends to infinity, I stop the Markov chain running and sample the state. The probability I will find in that state is d pi of s. What does it mean? I don't have any decision to make more. Now my pi is fixed after some steps. Like it is I can say this is a steady state distribution under the policy pi. Or in the next lecture, I'll tell you in detail about the steady state, or maybe I'll come up with some Markov chain and I'll tell you how we'll solve this, and I'll tell you the steady state stationary distribution and all, that how after some time steps it will not change and it will be steady in nature. The policy will be steady in nature, how this all is happening and how we are replacing it by d pi of s. Any doubts?
No, but just one question out of curiosity, that this reinforcement learning approach can solve better the traveling salesman problem has been tried or implemented.
I think yes, it can solve. It can. I'll look into it. I'll look once.
Okay.
We can discuss about it in next lecture. Yes, it can solve. Okay, I'll look into it. Like it can solve. We'll discuss about it in the next lecture. I'll look more.
Okay.
how it will solve. It can. Got the intuition somewhat?
Sorry.
I am saying you got the intuition behind everything.
Yes. It was nice. Means I understood.
Okay. So let me stop the recording.